Hey everyone, welcome to AirWise Academy, your trusted source for EASA Part-66 learning. Today, we're continuing our journey through Module 2, Physics, specifically in Submodule 2, Mechanics. We've now reached a fundamental and exciting section, Section 3, Dynamics. This section is packed with crucial concepts, and it's neatly divided into two main parts, Part A and Part B. First, in Part A, we will lay the groundwork by exploring core ideas like mass, force, and inertia. We'll then move on to understand the relationships between work, power, and the different forms of energy, such as potential, kinetic, and total energy. We'll also discuss heat and the important concept of efficiency. Then, in Part B, we'll shift our focus to momentum and the powerful principle of its conservation, along with the concept of impulse. We'll unravel the fascinating gyroscopic principles that are so vital in aviation. Finally, we'll examine friction, its nature, effects, and the critical coefficient of friction, including rolling resistance. For Part A of this section, which covers mass, force, work, energy, and efficiency, the requirements differ. If you are pursuing a B1 mechanical license, you need to reach Knowledge Level 2. For our B2 avionics colleagues, the requirement is Knowledge Level 1. However, for Part B, which includes momentum, gyroscopic principles, and friction, the requirement is the same for both groups, Knowledge Level 2 for both B1 and B2 licenses. So, let's dive in. Moving on to dynamics, we'll clarify the fundamental concepts of mass and weight, which are often confused. First, mass. Mass is a fundamental measure of the quantity of matter in an object. It is determined by the number of atoms or molecules it contains. Crucially, mass is constant. It does not change regardless of where an object is in the universe or if it changes state, like from a solid to a liquid. The only way to change an object's mass is to physically add or remove matter. Mathematically, mass is defined as weight divided by the acceleration due to gravity. In the imperial system, the unit of mass is the slug. An object with a mass of 1 slug will weigh 32.2 pounds on Earth. Conversely, a 1-pound force will cause a 1 slug mass to accelerate at 1 foot per second squared. Now, weight. Weight is not mass, it is a force. Specifically, it is the measure of the pull of gravity acting on an object's mass. The more mass an object has, the more it weighs under a given gravity. Because it depends on gravity, weight is not constant. It changes if the gravitational force changes. Its formula is the inverse of mass. Weight equals mass times gravity. A common misconception is that astronauts in orbit are weightless because there is no gravity. This is not true. Gravity is still present. They appear weightless because they are in a constant state of free fall around the Earth, creating a microgravity environment relative to their spacecraft. The key constant to remember is Earth's gravitational acceleration, which is 32.2 feet per second squared. This links the concepts of mass and weight together in our calculations. Let's now explore the concept of energy. In physics, energy is simply defined as the capacity to perform work. We can broadly categorize it into two types: potential energy, which is stored energy, and kinetic energy, which is the energy of motion. We will focus on potential energy first. Potential energy is energy at rest, waiting to be used. It can be stored in 3 primary ways. First, through position. Think of an airplane raised on jacks or water behind a dam. Second, through the distortion of an elastic object, like a compressed spring. And third, through chemical action, such as the energy stored in aviation fuel or a battery. To quantify the potential energy an object gains by being lifted against gravity, we use a simple formula. Potential energy equals its weight multiplied by the height it is raised to. The result is expressed in foot-pounds, which are also the units for mechanical work. This shows the direct relationship between stored energy and the capacity to do work. Now, let's look at a practical application. Consider a Boeing 747 that weighs 450,000 pounds and is raised 4 feet into the air for landing gear maintenance. Using our formula, we multiply its weight by the height. This gives us a staggering 1.8 million foot-pounds of potential energy. This highlights the significant stored energy that mechanics must be aware of for safety. Furthermore, we discussed chemical potential energy. Aviation gasoline is a perfect example. 1 pound of avgas contains 18,900 BTUs of heat energy. Since 1 BTU can perform 778 foot-pounds of work, we can calculate the immense work capacity of just a single pound of fuel, over 14.7 million foot-pounds. This illustrates the enormous potential energy stored in the chemical bonds of the fuel that fills an aircraft's tanks, which is converted into thrust and power. We now move from stored energy to energy in motion, kinetic energy. This is the energy an object possesses due to its motion, like an airplane accelerating down the runway or a spinning turbine rotor. It is crucial to note that kinetic energy shares the same units as potential energy, foot-pounds. This allows us to directly compare and calculate the transformation of energy from one form to another. The formula to calculate kinetic energy is 1/2 times mass times velocity squared. For this formula to yield a result in foot-pounds, we must use the correct units. Mass must be in slugs, which we find by dividing the object's weight by the acceleration due to gravity. Velocity must be in feet per second. Squaring velocity in feet per second and multiplying by mass in slugs results to the foot-pound units we require for energy. Let's apply this formula to a real-world scenario. Consider a Boeing 777 with a weight of 600,000 pounds during its takeoff roll, reaching a velocity of 200 feet per second. First, we must calculate its mass in slugs. We take its weight and divide by gravity, 32.2 feet per second squared. This gives us a mass of approximately 18,633.5 slugs. Next, we input the values into the kinetic energy formula. We take 1/2, multiply it by the mass in slugs, and then multiply it by the velocity squared, which is 200 times 200, equaling 40,000. Completing this calculation reveals that the moving aircraft possesses over 372 million foot-pounds of kinetic energy. This immense figure highlights the tremendous energy that must be managed by the brakes and other systems to bring the aircraft to a stop, underscoring the critical relationship between mass, velocity, and energy. Let's dive in the foundational concept of force, which is essential before we can understand work, power, and torque. Force is best defined as the intensity of an impetus. It's a push or a pull. When you apply a force to an object, its tendency is to move or accelerate. Crucially, for any of the subsequent concepts like work or power to exist, a force must first be applied to initiate the action. Force is measured in pounds in the imperial system and newtons in the metric system, with a conversion factor of 1 pound equaling approximately 4.448 newtons. The fundamental physics formula that defines force is Newton's second law. Force equals mass times acceleration. A prime example of force in aviation is jet engine thrust. The thrust value produced by an engine is a direct measurement of force. For instance, the GE90-115 engine on a Boeing 777 produces 115,000 pounds of thrust. This massive force is what accelerates the aircraft forward according to the principle of F equals m times a. We now move to the concept of work. In mechanical terms, work is not just effort. It has a precise definition. Work is only accomplished when a force acts on an object and causes it to move a certain distance against a resistance. The two factors are absolute. Both force and movement must be present. For example, if you push against an aircraft stuck in the snow and it doesn't budge, you may be tired, but according to physics, you have done zero work. We calculate work with a simple formula. Work equals force times distance. The units depend on the system of measurement. In the imperial system, Force in pounds multiplied by distance in feet gives a unit of foot-pounds. You will recognize this as the same unit used for energy, showing a direct equivalence. In the metric system, newtons multiplied by meters gives joules, where 1 joule equals approximately 1.36 foot-pounds. Let's apply the work formula with 2 practical examples. The first involves vertical work, jacking an Airbus A320 weighing 150,000 pounds to a height of 4 feet. Here, the force required is equal to the entire weight of the aircraft. Multiplying force by distance gives us 600,000 foot-pounds of work. The second example involves horizontal work, pushing a 737 weighing 130,000 pounds into a hangar. Notice the force required is only 5,000 pounds, just enough to overcome rolling friction, not the full weight. The work done is the tow force times the distance of 80 feet, resulting in 400,000 foot-pounds. This contrast highlights a critical point. The force in the work formula is the force applied in the direction of movement. Lifting requires overcoming the full force of gravity, while moving horizontally only requires overcoming friction, which is significantly less. This is why you can push a car but not lift it. We must refine our understanding of the work formula. The force F in W equals F times D is not always the weight of the object. It is the specific force required to overcome the resistance to movement. Consider this example. A 900-pound load on a cart is pulled 200 feet. The work done is not 180,000 foot-pounds. The person is only working against the rolling friction of the cart's wheels, which might be as low as 90 pounds. Therefore, the actual work done is only 18,000 foot-pounds. This introduces us to friction, a force with a dual nature. It is an absolute asset. Without it, we couldn't walk or take off. But it is also a liability that engineers must constantly fight to reduce in engines and moving parts to improve efficiency and reduce wear. Friction is not a single force. It behaves differently depending on the state of motion. Through experimentation, we identify 3 distinct types. First, starting or static friction. This is the initial force you must apply to break an object free and get it moving. It is always the highest value. Once moving, if the object is sliding, a smaller force is needed to maintain speed. This is sliding friction. However, if the object is on wheels, the force required drops significantly. This is rolling friction, which is always the least. This is why we use wheels and bearings in aviation, to minimize the force required for movement and thus reduce the work needed to overcome friction. Let's focus on static friction, which is the force that resists the initial movement of an object at rest. It is the breaking loose force and represents the highest level of friction that must be overcome. We calculate the force needed to start movement using the formula F equals K times N. Here, F is the force we need to apply. N is the normal force, usually the weight of the object pressing down, and K is the coefficient of static friction, a value published for different material combinations. For example, with a coefficient of 0.3, it would take a 3-pound force to start moving a 10-pound block. The key point is that static friction is the greatest. This is why it's a significant engineering challenge. A practical example is a train. A locomotive cannot overcome the static friction of all cars at once. Engineers solved this by backing up to take slack out of the couplers, then moving forward. This allows them to apply the force needed to overcome static friction to one car at a time, getting the entire train moving sequentially. We now examine sliding friction. This is the resistive force that opposes an object's motion once it has already been set in motion and is sliding. It is crucial to remember that sliding friction is always less than the static friction required to start the movement. The magnitude of this force depends on 3 factors: the nature of the 2 surfaces in contact and the normal force, which is the force pressing them together perpendicularly. On a flat horizontal surface, this normal force is simply the object's weight. We calculate it using the formula F equals mu times N, where mu is the coefficient of sliding friction. A critical and often non-intuitive principle is that sliding friction is independent of the contact area. The resistive force for a block of a given weight and material will be the same whether it is sliding on its largest face or its smallest edge. The force is distributed differently, but the total resistance remains constant. This brings us to the most efficient type of friction, rolling friction. This is the minimal resistance encountered when an object moves on wheels or rollers. It is the fundamental principle that makes vehicles and aircraft landing gear possible, as it is drastically lower than sliding friction. We use the same formula as for sliding friction, F equals mu times N. The key difference lies in the value of the coefficient mu. For rolling friction, these values are extremely small. For instance, the coefficient for rubber tires on concrete is about 0.02. For precision machinery like roller bearings, it can be as low as 0.001, a value so small it is often neglected in calculations. Let's apply this. To calculate the force needed to keep a 79,600-pound aircraft rolling on its tires over concrete, we multiply its weight by the coefficient 0.02. The result is 1,592 pounds of force. This example clearly shows why using wheels is essential for moving heavy objects like aircraft efficiently. We now move to the concept of power, which introduces a crucial new variable, time. Power is defined as the rate at which work is done. It answers the question, how long does it take to accomplish a certain amount of work? The formula is straightforward. Power equals work divided by time, which expands to force times distance divided by time. The unit of horsepower has a fascinating historical origin. Engineers wanted to market the new steam engine by comparing it to the standard source of power, horses. They defined 1 horsepower as the ability to do 550 foot-pounds of work every second, which is equivalent to 33,000 foot-pounds per minute. This standard, established centuries ago, is still used today to measure the power of engines, along with the metric equivalent of 746 watts. Let's apply this to a real aviation maintenance task, installing a massive turbofan engine. The goal is to lift a 19,000-pound GE Mindy engine a distance of 4 feet, and it must be done within a 2-minute time window. First, we calculate the total work to be done. Force times distance equals 76,000 foot-pounds. Next, we calculate the power required. Work divided by time gives us 38,000 foot-pounds per minute. To understand what this means, we convert to horsepower. Dividing 38,000 by the conversion factor of 33,000 foot-pounds per minute per horsepower gives us approximately 1.15 horsepower. This calculation clearly shows that this is not a job for human strength. It requires a powered hoist, as generating over 1 horsepower for 2 minutes is far beyond the capability of a person's arms. This is how physics directly informs the tools and procedures we use in aviation maintenance. Let's explore the concept of torque, a fundamental concept for understanding engines. While work involves a force moving through a distance to create linear motion, torque involves a force applied along a distance to create a twisting or rotational force. The formula looks similar to work. Torque equals force times distance. However, the critical difference is that this distance is the lever arm, the perpendicular distance from the pivot point to where the force is applied. Crucially, torque can exist without any movement. For example, pushing on a wrench attached to a tight bolt still applies torque to the bolt even if it doesn't turn. This is why the units, while similar, are written differently. Pound-inches for torque versus inch-pounds for work, highlighting this conceptual difference. Torque is the fundamental output of all engines. Let's see how different engines generate it. In a piston engine, the force comes from combustion gases pushing a piston. The connecting rod transmits this linear force to the crankshaft. The crankshaft's offset, or throw, acts as the lever arm. The product of the force and this lever arm is the engine's torque. In this example, 500 pounds of force on a 4-inch throw creates 2,000 pound-inches of torque. In a turbine engine, the principle is similar, but the force application is different. Hot exhaust gases exert a force on the blades of the turbine. The distance from the center of the shaft to where this force acts on the blades is the lever arm. This force acting along the lever arm creates the torque that spins the turbine shaft. While torque is a rotational force, horsepower is the measure of how much work that torque can do over time. They are not the same, but they are mathematically linked by the engine's rotational speed. The formula that connects them is torque equals horsepower times 5,252 divided by RPM. The constant 5,252 is derived from the definitions of horsepower and rotational units. Let's calculate the torque for a common training aircraft, the Cessna 172. Its 180 horsepower engine at 2,700 RPM produces 350 pound-feet of torque. This is the twisting force that is ultimately transferred to the propeller to generate thrust. This relationship is vital for understanding engine performance characteristics. Our discussion on efficiency must account for a major loss factor, heat. Beyond friction, machines often fail to convert input energy into output because a significant portion is lost as waste heat. For example, in an engine, energy is lost through conduction as heat is transferred to the cylinders, crankcase, and other components. This isn't just a byproduct, it's a fundamental challenge for any heat engine. The core of the problem is that the engine itself is always cooler than the explosive combustion gases it contains. This temperature difference means the metal components constantly act as a heat sink, absorbing and dissipating energy that was intended to perform mechanical work. Consequently, even the most advanced heat engines operate at around 50% efficiency. The average engine converts only 25 to 35% of its fuel's energy into useful work, with the rest being lost primarily as heat. This highlights a fundamental limitation in energy conversion. We now turn to momentum, a key concept in dynamics. Momentum is simply defined as mass times velocity. It describes the quantity of motion an object has. This concept is deeply tied to Newton's third law. When two objects interact, like in a collision, they exert equal and opposite forces on each other. This interaction leads to a fundamental rule, the conservation of momentum. This principle states that within a system, the total momentum remains constant. For example, if a moving object hits a stationary one, the first will slow down and the second will speed up. Their individual momenta change, but if you add them together, the total amount of momentum before the crash equals the total after. Nothing is lost. How is momentum changed? The answer is through impulse. Impulse is defined as a force applied over a period of time. The crucial link is the impulse momentum theorem. It states that the impulse applied to an object is equal to its change in momentum. We can derive this from Newton's second law. Force equals mass times acceleration, and acceleration is the change in velocity over time. Substituting and rearranging gives us F times t equals m times delta v. This means to change an object's momentum, you can apply a large force for a short time or a smaller force for a longer time. This principle is critical in aviation safety. For instance, an arrestor hook on an aircraft extends the time to slow down, reducing the massive force that would otherwise be needed to achieve the same change in momentum. Let's start with a fundamental question. What is a gyroscope? In simple terms, a gyroscope consists of a wheel or rotor, with most of its mass distributed along the rim. This rotor spins at high speed, mounted on bearings within a supporting frame. Now, let's look at different gyro configurations. In figures A and B, we see a captive gyro. Here, the rotor spins on one axis and is free to rotate about one other perpendicular axis. It's mounted in a single ring with brackets, limiting its movement to one additional plane. In contrast, figures C and D show a free gyro. This type is mounted within two gimbals, an inner ring and an outer ring. This structure allows the rotor to spin on one axis while remaining free to rotate about two additional perpendicular axes. It's this free gyro configuration that forms the basis for many critical flight instruments, thanks to its greater freedom of movement and stability. Moving on to the fundamental properties of a gyroscope, we come to the first and most important one: rigidity in space. This principle states that a spinning gyroscope will maintain a fixed position in space. Once its rotor is spinning at high speed, the spin axis will remain pointing in the same direction, regardless of how the base or the surrounding framework is moved or tilted. You can visualize this with the figure, which shows how the gyro's base moves, but the rotor's axis stays locked in its original orientation. Now, the strength of this rigidity isn't absolute. It depends on several key factors. First, the weight of the rotor. A heavier mass offers greater resistance to deflection. Second, the angular velocity. A higher spinning speed significantly increases rigidity. Third, the weight distribution. Concentrating the mass at the rotor's rim maximizes the gyroscopic effect. And finally, bearing friction. Lower friction minimizes the external forces that could cause the gyro to drift. This principle of rigidity in space is not just a theoretical concept. It has critical applications in the cockpit. It is the fundamental operating principle behind attitude indicators, which show the aircraft's orientation relative to the horizon, and directional gyros, which provide a stable heading reference. We now arrive at the second key property of gyroscopes: precession. This is the unique reaction of a spinning gyro when an external force is applied to it. Unlike a stationary object, a gyroscope does not simply tilt in the direction you push it. Instead, it responds by rotating as if the force had been applied 90 degrees later, in the plane of its rotation. This concept is clearly illustrated in the figure. Notice how the applied force, the gyro's own rotation, and the resulting movement, the precession, all exist in three separate planes that are perpendicular to one another. This predictable behavior is not just a curiosity. It has practical applications. It is the working principle behind the turn and bank indicator in the cockpit. Furthermore, precession is a critical consideration in aircraft design and operation. Any large rotating mass, such as a propeller or a turbine engine, acts as a gyroscope. Engineers must account for the precessional forces these components generate, as they directly influence the aircraft's handling characteristics during maneuvers. And that brings us to the end of this lesson for today. Now, let's warm up with a few questions to review what we've learned. Now, let's get started with question 1. Which of the following statements about mass and weight is correct? A. The mass of an object changes if it is taken from Earth to the Moon. B. Weight is a measure of the quantity of matter in an object. C. An object can be weightless if it is in a state of free fall, even though gravity is present. The correct answer is C. This statement is accurate because weight is the force of gravity acting on a mass. During freefall, like the astronauts in the space shuttle, the object and its container are accelerating towards Earth at the same rate. This creates the sensation and appearance of weightlessness relative to their environment, even though gravity is still pulling on them. Question 2. An aircraft weighing 80,000 pounds is lifted 6 feet off the ground for maintenance. Using the formula for potential energy, calculate how much potential energy the aircraft gains. A. 480,000 foot-pounds. B. 86,000 foot-pounds. C. 1,800,000 foot-pounds. The correct answer is A. 480,000 foot-pounds. Let's look at the calculation shown on the slide. We use the standard formula for potential energy due to position. Potential energy equals weight multiplied by height. The aircraft's weight is 80,000 pounds and it is raised to a height of 6 feet. Multiplying these two values together, 80,000 pounds times 6 feet, gives us a result of 480,000 foot-pounds. This is the amount of stored energy the aircraft has in its raised position. Question 3. A maintenance crew uses a tow tractor to push an aircraft weighing 90,000 pounds into a hangar. If the force required to move the aircraft is 2,500 pounds and it is pushed a distance of 60 feet, how much work is accomplished? A. 135,000 foot-pounds, B. 150,000 foot-pounds, C. 5,400,000 foot-pounds. The correct answer is B. 150,000 foot-pounds. Let's perform the calculation. The formula for work is force multiplied by distance. It is crucial to note that the force in this case is not the weight of the aircraft, but the actual force needed to overcome friction and move it horizontally, which is given as 2,500 pounds. The distance moved is 60 feet. Multiplying the force of 2,500 pounds by the distance of 60 feet gives us a result of 150,000 foot-pounds of work done. Question 4. Which type of friction requires a greater force to overcome? A. Sliding friction, B. Rolling friction, C. Static starting friction. That's right. The correct answer is C. Static friction. As we learned, static friction is the force that resists the initial movement of an object from rest. It takes the most effort to get something moving. Once the object is sliding, the resistance decreases to sliding friction, which is lower. Rolling friction, found in objects with wheels, is generally the smallest of the three. So static friction is always the greatest challenge to overcome. Question 5. If the coefficient of static friction for a metal block on a ramp is 0.4 and the block weighs 50 pounds, what is the minimum force required to start moving the block? A. 20 pounds, B. 125 pounds, C. 50 pounds. The correct answer is A. 20 pounds. Let's work through the calculation together. The formula to find the force needed to overcome static friction is the coefficient of friction multiplied by the normal force. In this case, on a horizontal surface, the normal force is equal to the weight of the block, which is 50 pounds. The coefficient is given as 0.4. So, we multiply 0.4 by 50 pounds, which gives us a result of 20 pounds. This is the minimum force required to overcome static friction and get the block to start moving. Question 6. A maintenance crew needs to lift an aircraft component weighing 8,250 pounds to a height of 2 feet. The task must be completed in 30 seconds. How much horsepower is required for the hoist to perform this task? A. 0.5 HP, B. 1.0 HP, C. 2.0 HP. The correct answer is B. 1.0 horsepower. Let's go through the solution step by step. First, we calculate the power required. Power is work divided by time, and work is force times distance. So, we multiply the weight of 8,250 pounds by the height of 2 feet, which gives us 16,500 foot-pounds of work. This work must be done in 30 seconds. Dividing 16,500 by 30 seconds gives us a power requirement of 550 foot-pounds per second. Now, to convert this to horsepower, we use the conversion factor 1 horsepower equals 550 foot-pounds per second. Dividing our power value of 550 by the conversion factor of 550 results in exactly 1.0 horsepower. This means the hoist needs an engine rated for at least 1 horsepower to lift the component in the required time. Question 7. A turbine engine produces a torque of 400 pound-feet at 3,000 RPM. Using the relationship between horsepower and torque, calculate the horsepower developed by the engine. A. 175 HP, B. 228 HP, C. 350 HP. The correct answer is B. Approximately 228 horsepower. Let's perform the calculation together. The formula that links horsepower and torque is horsepower equals torque multiplied by RPM divided by the constant 5,252. The torque is given as 400 pound-feet, and the engine speed is 3,000 RPM. First, we multiply the torque by the RPM. 400 times 3,000 equals 1,200,000. Then, we divide this result by 5,252. This calculation gives us approximately 228.5 horsepower. Question 8. According to the principle of conservation of momentum, what happens to the total momentum of two objects when they collide? A. The total momentum increases. B. The total momentum decreases. C. The total momentum remains the same. That's correct. The answer is C. The total momentum remains the same. This is a fundamental principle in physics. When two objects interact, like in a collision, the momentum of each individual object will change. One might speed up while the other slows down. However, the total momentum of the system, meaning the sum of the momentum of both objects, is conserved. It stays constant. Think of it as momentum being transferred between the objects, but the overall amount doesn't change. Let's quickly see why the other options are not correct. Option A and Option B suggest that momentum is created or destroyed during the interaction, but the principle of conservation tells us that momentum cannot be created or destroyed, only transferred. Question 9. What is the key characteristic of a spinning gyro that allows it to be used as the basis for an attitude indicator? A. Precession. B. Rigidity in space. C. Bearing friction. The correct answer is B. Rigidity in space. This fundamental property means that the spin axis of a freely rotating gyro will maintain its fixed orientation in space, regardless of how the aircraft maneuvers around it. This stable reference is exactly what an attitude indicator uses to show the aircraft's pitch and bank angles relative to the horizon. While precession is another important gyroscopic property, it is not the principle used to establish the stable reference for attitude indication. Question 10. If a pilot applies a force attempting to tilt the spin axis of a rapidly spinning gyroscope, how will the gyro actually respond? A. It will tilt in the direction of the applied force. B. It will resist the force due to rigidity in space and not move. C. It will rotate, precess, as if the force was applied 90 degrees later in the direction of rotation. The correct answer is C. This describes the phenomenon of precession. Instead of tilting in response to the applied force, the gyro reacts by rotating around an axis perpendicular to both the spin axis and the axis of the applied force. It behaves as if the force was applied at a point 90 degrees further around the rotor's rotation. Option A is incorrect because the gyro does not simply tilt. Option B describes rigidity, but a force will cause a response, it just isn't a direct tilt. That's all for today's lesson. If you found this video helpful, please give it a thumbs up and consider subscribing to AirWise Academy for more aviation knowledge. We'd love to hear your thoughts or questions in the comments below. Turn on notifications so you won't miss our upcoming videos. Until next time, blue skies and happy learning.